Hello, everybody, and welcome back to the Design Well podcast. I'm Nick Bover, editor of Design Well 365, and thank you for joining me today. In the realm of construction and architecture, mass timber, also referred to as cross-laminated timber sometimes, has become a new and exciting material for many professionals that offers more sustainable options for building over traditional building materials like steel. However, the material is not without its limitations. This has led to firms like DIALOG in finding ways that can improve upon these limitations with building innovations like their new hybrid flooring system, which has just wrapped up its first round of testing. Joining me today is Craig Applegath, partner and architect at DIALOG, who has helped develop the new mass timber flooring system aimed at taking sustainable building to literal new heights. So without further delay, let's dive right into our conversation.
Thank you for tuning in. If you liked what you saw, be sure to hit the like button on your way out, and also subscribe to DesignWell's YouTube channel and hit the bell icon if you want to stay informed of any new updates. Alternatively, you can find any of our podcasts over on Apple or Spotify and leave a review there.
Before we get into it, Craig, I'd like to let you introduce yourself first.
Yeah, sure, Nick. I'm happy to be here and give your listeners some idea of who you're talking to. I am an architect and designer, and I focus on zero carbon buildings and buildings that are meeting the challenges of climate change impacts. I trained as a biologist before going to architecture, and then I also did a degree in urban design at the GSD at Harvard. So I bring all that together in my current practice. As you said, I'm right now leading a group of integrated disciplines: architecture, planning, landscape design, mechanical, electrical, structural, for a hybrid wood prototype tower that you mentioned. And part of that tower is a new patent pending timber floor system. And we can talk about both of those if you like. And I've been practicing now for over 25 years. My typical area of practice is post-secondary education projects. Mass timber projects I get involved in because I'm passionate about mass timber because of its implications for locking up carbon and reducing embodied carbon. So that sort of gives your listeners some sense of who you're talking to.
Great. Yeah, it's kind of interesting that you started off in biology before moving over into the architecture. Was that kind of passion for biology sort of what guided you towards the sustainability later on down the line?
Well, I started out of high school. I was interested in design and making and building things. I've always been building projects at sea my whole life, but I have always been really, really interested and attracted to things, natural systems, biology, botany, and so forth. I had aquariums when I was a kid. I hatched ducks and geese, all sorts of things. And so when I got into biology, I enjoyed it, but I realized I wanted to be a 19th century biologist. And sort of discover the world of natural systems as opposed to fight for research funding to write papers. And it just the life of an academic, I looked at it when I was there and thought, oh, I don't think this is for me. And so I started thinking, okay, what are some of the other things I was interested in? And making things and designing things was one of them. And a friend of mine from high school, who's now a well-known Canadian architect, Bridget Shim, I bumped into her in the cafeteria and we got talking, and she'd just gotten into architecture school. So it sounded really interesting. And the more I looked into it, I thought, why didn't I know more about this? So I went into architecture school, and it was like dying and going to heaven. It was just wonderful. I enjoyed every second of it. And I've enjoyed almost every second of my career. I won't say every second. There's always
that's how you know you love a career, though, where it's like there's those moments. It's not butterflies and sunshine all the time.
No, it's definitely not. But you know what? I think if you like designing, and if you like making things, and if you like working with people to make things happen, architecture, engineering, planning are wonderful careers to have. It's challenging. Every career is challenging because you're working with people, and people have their own points of view and their own directions. And you, as an architect, you're pulling people together to try and make things happen. But it is a wonderful, wonderful opportunity. You know what's really weird, Nick? When I started interviewing architects to see if I want to go in architecture school, I would say that at least 5 out of 6 or 7 of them told me it was a terrible career to have. And I thought, how weird is that? Like, what are you doing? And I, when you're in your 20s, you know everything, and it doesn't matter how experienced a person is. You figure you know better than they do. So fortunately, I didn't listen to them, and I went into architecture. Anyway, so what I'm doing right now, the buildings I'm doing, the hybrid wood tower, and we're working on a building that's literally being constructed right now. The Centennial Block A building, which is a hybrid, which is a mass timber, not hybrid, it's a mass timber building, zero carbon. These are all buildings that required all of the skills that I've learned over the last 20 or 30 years, not only in architecture, but also in biology. And so I think now things are starting to come together just as the world's coming apart at the seams.
That's really curious, because I kind of my career path was on like a similar trajectory, just to kind of get off topic a little bit, just in the terms of the sciences going into the arts. I originally started off in chemical engineering and then kind of shifted over into English, and yeah, but kind of owing to what you said, it's interesting where, I really liked the sciences. I really liked all of the innovations that were going on in the sciences. But it was something where the kind of academic, sitting at an office wasn't really too much for me as I got deeper into it. And eventually, later on down the line, I had the same reaction. I always liked writing, so maybe I can get into writing. And everybody was telling me, yeah, it's going to be very hard. I'm like, you know what? I'll just do it anyways. It's like, it's fine.
Love it. It's funny you mentioned chemistry. I have really not good memories of chemistry for 2 reasons. One was everyone in science, except like 3 of us, were trying to be doctors. So it was hugely competitive. And in chemistry class, the numbers of the students, so these are people that you're going to want to trust with your life later on, were sabotaging other people's experiments. It's like, no, this is not right. This is terrible. At least that was in organic chemistry. Anyway, so you're probably better in English.
Yes. And it turns out that later on down the line, the position that I'm in currently, talking about these different types of innovations, talking about building sciences in general, that kind of like science, analytical background has definitely helped me out a lot in being able to cover these different types of topics. But with that being said, and not to get too far off topic, I figure we can jump on into the basically the task that you guys have at hand. And I think it would be beneficial for somebody who's not too familiar on mass timber design to know, what has prevented mass timber from being used in these like super tall structures to this day?
Okay, so can I just back up a little bit, back the question a bit, because I'll bet some of the listeners don't actually know what mass timber refers to. So why don't I just give a little primer on what mass timber is?
Yeah, go ahead.
Way back in the 19th century, when they were building buildings, typically the structure was timber frame construction, the early 19th and 18th century, and then masonry wall construction. So the outside walls were like 2, 3, 4, 5 feet thick, and they went up, and then they supported big, huge timbers like beams, and then there'd be big columns, and they were made from big trees. Like in Europe, they'd be big oak trees. Here, they might be Douglas fir trees. And so then in the later 19th century, they started using steel as columns, but they typically continue to use the floor as timber. So that would be what's called nail laminated timber. They take the 2x6s on their end, and they lay them down across the beam, and they nail them together. So they became a complete solid floor system, nail laminated timber. So that was pretty much how all buildings were built until the early 20th century, where they started to use this amazing stuff called concrete, which was amazing because you put rebar in it, and it had great compressive strength and also great tensile strength. And they could either support the concrete floors with steel columns or concrete columns, reinforced concrete columns. So that became the modern construction methodology, and it is still the standard construction technology. The tall buildings are typically steel construction with a concrete core being where the elevators and fire stairs are, exit stairs. Medium tall buildings are often all concrete. So timber disappeared because it was more artisanal. You could move faster with steel and concrete. And more importantly, you could go taller because of the capacity for concrete and steel to take compressive load. So if you went up really, really tall with a wood building, most of the ground floor would be wood because the cross section of timber required to hold that load above it is huge, whereas concrete or steel, it's very, very small in comparison. So it disappeared basically as a building material system. Until recently, where we've started to look at the embodied carbon attributes of building materials because of climate change. And embodied carbon, for your listeners that don't know, is all of the carbon dioxide that's released in the process of getting the materials from wherever they're manufactured, dug out of the ground, whatever, transported, CO2 released during transport, CO2 released during construction. That's considered embodied carbon. Operational carbon is the CO2 released when you're heating a building or cooling a building. So, wow, buildings are filled with a lot of concrete and steel, and those are both really, really intensive carbon efforts, right? Like concrete releases a lot of carbon dioxide when the cement is made. Steel releases it when the steel is made. So it's like, okay, well, timber is this amazing stuff because A, it locks up carbon, stores it, and B, to get the same amount of strength out of timber, it's a lot less carbon. So how do you do that? Well, for the last 10 years or so, you've been hearing a lot about mass timber. Well, mass timber, it means that you take smaller pieces of wood, so imagine 2x4s, and you glue them together. And to make a column, you've probably heard of glue laminated columns. Well, it's a number of pieces of 2x4, 2x2s, whatever, glued together under pressure and then milled to make the shape. And that gluing together allows you to create much bigger section. By section, I mean the width by the depth of the member. So the other thing that's just happened to be really started to evolve over the last 10 years is what's called CLT, cross-laminated timber. So imagine, your listeners imagine you lay out a series of 2x4s on the manufacturing deck, and then you pour glue on them, and then you lay 2x4s at 90 degrees to them, make a layer, and then lay glue on them, and then again 90 degrees to that, and back and forth, 5, 6, 7, 8 times, and you build yourself a section that's like giant plywood, right? It's got these layers all glued together. So the layers allow you to have the tensile strength as well. So here's the thing: you can make at the outset about 30-foot span of CLT, cross-laminated timber floor. But office buildings, commercial office buildings have a span that real estate folks want for leasing purposes of about 40 feet, 40 to 45 feet. So you can't use CLT unless you have intermediate columns. Well, that gets in the way of how offices are laid out, and so tenants don't want it. So there's this, personally, I think it looks great, but it's an issue. So about 4 or 5 years ago now, my partners and I were just in the process of finishing up doing a low-rise CLT building, zero carbon CLT building, really cool. And I said to them, hey, I think we need to do a really tall building. And they said, yeah, but you can't do tall wood, Craig. I mean, they're engineers, right? So they know the problem with wood. I said, we can figure it out. And they're really polite, so they didn't say you're just a dumb architect. Which is probably, I could see in their like face, like if only understood. No, I get it. But so I said, no. I said, what is it with this culty religious nonsense about pure wood? Like everyone's trying for the tallest mass timber building right now around the world. And you got at 20 stories somewhere in Norway, right? And you've got a few proposed buildings that are all wood that are much taller than that. But it's like, why all wood? They're not all wood. They're like the joints, the connections are stainless steel, and they're built on concrete foundations. So it's not all wood, really. It's just like, we know you're using how much steel. It's just a question of how much of it. So I said, well, look, let's analyze a building. And in a building, a tall building, what I didn't realize until we did this and the light went bing in everyone's head at the same time, Nick, was 70% of a building's material content is floor systems.
That is surprising. I was not aware of that.
70%. I'm like, that's it. Why don't we just do a standard tall building with a steel exoskeleton and a concrete core, and we'll figure out how to do CLT floor systems? Duh. And then it's like, yeah, but remember the problem of the width. So I said, well, what do we do? Like, is there a hybrid CLT system we can figure out? So we got working on it, and what we came up with as a solution, and it's now a patent pending solution, is you take that CLT that I was telling you about, you flip it over, and you basically route out a long strip the strips will run from the core to the exoskeleton. And in that slot, it's like about 2 inches wide and 2 inches deep. You put rebar, post-tensioned rebar, and concrete. And that basically provides tensile strength. So you've got the long panels with tensile strength. Same thing you do with concrete, right? Concrete would just fall apart if it didn't have the rebar. Like when you put rebar in a floor system of concrete, it's at the bottom 2/3 mark of that section. So we're doing the same thing, only we're doing it with wood. Done. So we could do. And we said, well, how tall? I said, well, no one is even going to pay attention unless it's 100 stories. So we said, well, why don't we do 105? Well, we started with 120 and said, well, you know what? People will probably think it's insane. So like, okay, 105? So we could go taller. But the point is that it's a hybridization. It's using the wood in a way that is not pushing the envelope really. I mean, that rebar system it's not out of this world in terms of its realization.
I was going to say it's tried and true at this point.
We're building it right now. We're building the timber floor system right now. In order to, you have to get code approval, you have to be able to test it in bending. So you span it between a rig in a testing factory, and they put pressure down on the middle. So they test. Is it going to bend the way you say it will, right? All the calculations are there. It's been computer modeled. It should work. Let's test it. And then there's another one called creep. And creep is over time, wood settles down a bit, like the fibers move a bit, one against the other, they stretch out a bit. So you test the creep calculations you've done, are they reasonable? And then finally you burn it. And this CLT has what's called a sacrificial layer of 2 inches of wood. And when a fire starts, it chars and prevents the fire from getting higher. So
interesting.
That's happening right now. So this is very doable.
Huh. Yeah, that's really incredible. You honestly, the entire time, like running through it, it's like I kept on having my questions like pop up in my head, and you kind of knocked them all out. That's really incredible. Just the amount.
Well, I think it's because the questions popping up in your head, Nick, were the same questions popping up.
Yeah. Throughout the entire process.
Well, what about this? Well, what about yes, exactly.
Yeah, exactly. I actually just got off of and the thing is, like, I just recently got off of I just came back from KBIS and the International Builder Show.
Yeah.
So that all of that's kind of at the forefront of my mind already. And that was kind of a lot of that was really the talk of the town out in that section, you know, being able to come up with not just, you know, wooden cladding or just like wooden building materials, but finding out ways in which, you know, these wooden building materials, one of the primary concerns in a building is, well, what happens if a fire gets started? And
yeah, and a lot of people are afraid of wood because of fire. And in fact, one of the great things about being part of an organization like Dialogue is it's integrated. So I'm constantly working with structural engineers, mechanical, electrical engineers, material scientists, and so that you're questioning and supporting one another, and the ideas develop together. They don't develop in isolation of one another. So one of my concerns immediately, like 10 years ago when I started to explore mass timber, was, well, what about fire? Like I have a fireplace, I burn logs, like isn't gonna, well, then there's the whole reality of charring and how that is accommodated. And most people don't understand that steel is actually really, really dangerous in a fire because it loses its tensile strength. It sags. So steel buildings will fall apart very, very quickly in a fire. Even, I mean, after the fireproofing has burned off, then the steel collapses. So you right now with a steel building, you have X number of minutes to get out. That the fireproofing is for safety, for getting people out. It's not to stop the building from collapsing. I mean, granted, you're trying to put a fire out with fire suppression, but in terms of the actual problem, I mean, you saw what happened with the World Trade Center.
Yeah. So I guess kind of following it up with some of the questions about the general process itself when it comes to building this new technology. Part of what I read on this project was that you had a construction partner, Ellis Dawn, working with you.
Yes.
And I was very curious about, you know, what it was like working with them, because I actually have, you know, personal anecdote here. I have a father who works in construction, and he is constantly complaining to me that like he wishes the architects would talk to the construction crews a lot more on these types of projects. So I was wondering what your collaboration with Ellis Dawn was like.
So first of all, let me speak to why your father would say that. Because when I was a very, very young architect, the world of construction and the world of architecting were very separate. And architects saw themselves as being superior to constructors. And the constructors were there to service the architects' architectural desires. And typically it's because the construction world was not typically a sophisticated, educated world. There were very sophisticated people in it, but that was not the sort of nature of the beast. Today it's different. If I look around the room in a meeting, say with Ellis Dawn, every person there, every man and woman has an iron ring. In Canada, I don't know if they do it in the States, but engineers get rings when they graduate.
Oh, interesting.
It's to represent a bridge that fell down and the responsibility. They're engineers, they're MBAs, they're material scientists. The Ellis Dawn has 50 people in its construction sciences group. Like it's a totally different world. In fact, Ellis Dawn has 100 people writing code. They develop their own software. Like it's like working with a university, right? Like it's a different game altogether. So when we were starting with this tower, Ellis Dawn was working on another project I was working on in mass timber, and I said to them, like, let's take some of the knowledge we're developing together as a group and apply it at this incredible level here. This is going to be something that will make some waves. And so their contribution, and it was totally collaborative. We took the idea as a very basic idea, was about logistics and constructability. Like, not will it go together, but what's the most efficient way of putting this on the site? So what are the size of the panels? Because you've got to lift them up in the air with a crane, and you got to truck them from the manufacturing site to the construction site, and you got to do it in a way that works with all the trucks and stuff. So what are the size of the panels? What can they be? And they can only be of a size that the crane can lift them, because wood, that thickness of wood is quite heavy. So they were doing logistics. They were doing calculations in terms of what is the most effective way to build this. Like not just to get the structural specifications right, but to actually make it so that it's affordable. And because all of this is not going to make any difference if it just stands up, but no one's going to build it. And that's one of the beefs I had with the religious gang that want all wood buildings is, fair enough, but who can afford it? Why not have buildings where we really can get the wood into the buildings in a way that's economically viable? Because otherwise it's just a dream. Or it's going to be institutions that can do a small building, like a 4 or 5, 6 story building, that makes sense, but tall buildings, it just won't work. So Ellis Dawn was right there, and 2 young engineers, Mark Gallioni and Vince Davenport, sort of worked on our team. Like, we were back and forth, but before COVID, in each other's offices and studios, sort of developing the actual building. So this was a totally collaborative event for the building design. But then when we started to put the patent together for the floor panel system, it was a 50-50 partnership of developing this together.
Yeah, I really get what you're saying with the finding out a way to build it efficiently on site, and keeping the cost within range. Because I mean, obviously when you're talking about embodied carbon, the one thing that you really want is to make sure that it's not too complicated to build, because that's one of the whole things that you're trying to tackle in the first place. And then on the the cost side, I actually just heard recently, it was, I think, Lawrence Berkeley National Laboratory, way back in the 90s. You probably know what I'm talking about already. They had developed, just a very simple 3-pane glass system for a window in order to cut down on, heat transfer through the window. Right. And for the longest time, it was never used. And only recently it's starting to get used again. And the reason being is that it was just way too expensive. Nobody wanted to produce it. But since we have all of this technology being used that uses this type of ultra thin glass that the original design was using, drove down the prices, and now it's a lot more affordable. And now companies are actually starting to produce these types of windows.
Yeah, I think what you're talking about are economies of scale, and what all of the. By the way, when we did the calculations for the hybrid wood tower, the tower itself altogether in terms of cost, it was around 10 to 15% more than a normal like a steel tower. When talking to developers, they thought that they could at least accommodate 5% because people wanted it more. This is with mass timber being totally new. Like, competition is going to drive down prices. So this is going to be cost competitive in a heartbeat. Like, it's not going to be long.
Right. I guess kind of moving forward with, we kind of discussed, you already went into a lot about like what went into the testing for this type of product, but I guess the other aspect for it was the funding rounds, and I'm kind of curious as to what the process was like. And I'm sure people who are not really versed in having to get funding for these types of innovations, they'd probably be a little interested too into like what went into trying to secure funding.
Okay, so we're at the point where we're just dealing with seed money. We haven't done any Series A funding. We have basically self-financed this up until right now for testing. And testing is quite expensive. It's hundreds of thousands of dollars. So we have gone to get grants from a number of granting agencies in Canada that are supporting the development of mass timber. So they're going to be helping finance or pay for the testing, the burning, the bending, and the creeping. So that is like a pre Series A, so it's still seed. And DIALOG and Ellis Dawn have self-funded. And we did it because not just because we're thinking this timber product will be something that will be hugely marketable, which I think it will be. We did it in the beginning because we are always looking for ways to demonstrate to our clients that we can add value to them. And the only way to do that is to do innovative work that involves research, work that is sort of at the cutting edge. So you have to fund that research yourself. And as I said, the construction industry is now very sophisticated. They're in the same business. They've got to demonstrate their sophistication. So we both teamed up and said, okay, this will make sure that when a mass timber project happens, we're going to have an opportunity to go for it, because guess what? We're the world leaders in the tallest mass timber building in the world. Right? So, and we're learning. And guess what? There's another really amazing thing. Like, don't you think every single architect and engineer wants to come to a firm or wants to come to a construction firm doing the coolest stuff in the world? Yes. And how do you do great projects unless you have the best people in the world? You don't. Like, it's you constantly got to be doing the coolest, most innovative, most thoughtful, the most aggressively forward-looking work in order to have the best people, and the best people will do the best work. So it's like a virtuous circle. So that was the original incentive to do this, is just to keep sort of ahead of the curve. And then out of it came this cool patent. We're like, okay, this is great. Something's actually come out of this cool innovation. So it's bonus.
Really, really does highlight just the power of partnerships in this day and age. I feel absolutely. Like, yeah, because the way you're making it sound, it's almost like you probably wouldn't have been able to do it without Ellis Dawn.
Absolutely, we were able to do the sort of conceptual structural design, but we would not have been able to do it to make it a real thing, to make it, something that you could bring to a developer and say, we've tested. Because if we walked into a developer with it, they go, that's sort of interesting. When we walk in the door with Ellis Dawn and they lay out the logistics, then the developer's like, yep, okay. When do we start? Well, we can't, because we gotta do the testing before we can get the code approval and so forth. But yeah, and I just think, by the way, Canada is not an exception. In the States and Europe too, it's the industries are completely integrating in terms of their competencies and intelligence, abilities to collaborate, abilities to innovate. And the world of separation is something so far in the past now. And anyone that not understanding that it's not good.
was going to say, it's definitely something that I personally am very glad to see in a lot of cases, because yeah, just from having my own father as a construction worker, and, having multiple friends who are in the trades. And I even have one that's like super into building sciences alongside me, and passive house building in general, where it's like you kind of have all of these different ideas that are kind of like entering into different spheres at any given time. And then there's also just the matter of, you can have the very lofty ideas like we were talking about earlier, but then you kind of really need to get down to the ground level and say, okay, but what's the practicality of this? And it's always great to be able to have these different firms that are working on construction communicating with one another, so that, it's almost like a checks and balance system in a way.
Yeah. And also I think, and by the way, mass timber is special also because there is a craft there as well, that it's sort of completely new, but it's very ancient at the same time. Have you been in a mass timber building recently?
I honestly don't think I have.
So poke your nose in, because what you'll realize is you can feel it, you can smell it. It smells wonderful. It's like being in a forest. It's just, you're like,
I feel like I would love that.
You really you go, it's wonderful. They're just
I mean, that just ties right into the whole biophilia craze that's going on too.
Absolutely. And this, by the way, caveat.
Mm-hmm.
If mass timber is made from sustainably harvested timber, and that's another podcast worth of discussion, it's good. If it's from clear cut, it's a freaking disaster. So it's not that wood is good, it's that wood sustainably harvests, so it actually improves the ecology of the forest it's taken from, is good. And by the way, some really interesting, some you might want to talk to in a future podcast, is the really fascinating work being done with blockchain and DNA to sort of figure out, well, how do I know that this mass timber is coming from where they said it's coming from, right? Like, what's a provenance of this? What's a chain of custody? And so if you have blockchain and DNA, you could probably, where it's come from. Anyway, that's that. So the most ancient of building materials transformed to the most sophisticated of building materials. It's a very interesting transition.
Yeah, that's very interesting. I feel like we're probably reaching the limit of our time here. I don't want to hold
special wrap-up questions.
Well, I figure I had one question that kind of popped into my head earlier on, and then I'll hand it off to you for any closing comments if you have any. But one of the things that I was curious about is how long has the testing been going on up until this point? How long have you guys been kind of like testing the prototype for this flooring system?
Well, we've been designing it, like testing it on computers, because now everything gets tested through computer modeling for the last 2 years. The physical testing, where we physically build panels and bend them and creep them and burn them, is just starting right now.
Oh, okay. So you're just at the cusp of that.
Yeah. I mean, the iceberg, the tip of the iceberg is sort of the testing. All the other research is below that. So once it's tested, that's the next phase is then getting a code approval and doing the kind of work required in order to get this thing to be marketed. By the way, you don't have to have this in a tall building. You can have it in a 2-story building, right?
Right. So I guess the question then is, like, if the actual physical testing is such a small component of it, and you've already put 2 years into kind of like all of the research and development of that, how barring everything goes according to plan, how long do you expect the actual like testing to take?
That's a good question. Probably somewhere in the range of about a year.
Okay.
Results back. So it will vary depending on because of COVID and because of the plants. I'm I'm hesitant to make a commitment right now.
I was going to say, are you running into, do you foresee there being any problem?
Yeah. Well, we don't know, right? Like who would have known there was going to be a trucker strike that would hold everything up and shut down the automobile plants near Windsor? Like, anyway, a yearish or so.
All right. Yeah, no, I was just curious about that. It was something that kind of like popped into my head because I myself am not privy to the ins and outs of the testing process when it comes to something like this.
What's fun? Make a good podcast.
Yeah, definitely. And I guess, we kind of covered, because the only other question that I had would be, if you had any advice to give to people who were, say they were working with their own firms and trying to do exactly what you're doing, just in terms of trying to push forward, innovate, come up with these new ideas, how you would kind of advise them moving forward, just from either a, partnership standpoint or from a funding standpoint?
Well, from a sort of a process standpoint, I would say that innovation is a team sport. If they want to really get a great sense of how innovation works, there's a wonderful book called Where Good Ideas Come From. And one of the things that was set out in it is that the history of innovation is almost 50-50 divided between individuals, like Edison coming up with an idea, versus groups of people coming up with an idea. I think the complexity of, and if you're talking about ideas like construction ideas and design, you're going to have to be working with a sophisticated team. So you want to be in some sort of integrated team where you've got architects and engineers, material scientists, building scientists. I would team up with a sophisticated contractor, a constructor. So you really do want all those insights. That doesn't mean you don't start with some ideas and a doodle on the back of a napkin, classic architect thing to do. But in order for that to actually come to fruition, there has to be different kinds of insights brought to bear. Like my idea about the tower would not have happened if we didn't have my partners, Daria Kachi and Thomas Wu, structural engineers, and we sat down over a glass of red wine, 3 glasses of red wine, and then talked about how you would actually do this. And the ideas went back and forth very, very quickly. And a sketch emerged, literally, that evening. There was a sketch. And so I think that wouldn't have happened if you had any one of us there, but the insights coming together from a group of people is very, very powerful. And so I'd say, if you're a young architect or a young engineer, start building what I call your neural network. Everyone talks about networking. Well, I think in our very, very complicated, sophisticated world, you need to build a group of friends and colleagues that are your neural network to help create, build, give ideas some future. And that's probably the most important thing to do.
Yeah, that sounds great. It definitely echoes a lot, is because at the end of the day, it's all, you're designing something. It's, as you kind of described, it's a bit of an art form in and of itself. And, it's a mixture of art and sciences almost. And I can say from the art community, just going to English school for so many years, it is kind of all reliant upon building that connection of people there. And I can even say that with the limited amount of schooling that I did in chemical engineering too, all of it was based on, any class that we had to do. It's working with other people to build these designs.
Yeah.
And so that's really great. Before we head out, is there anything that we missed that you would like to add?
No, I think we've covered everything. Just to reiterate, the power of collaboration for innovation is something that's really, really important. And also, I'd suggest the importance of trying to step outside current paradigms and really examine them carefully. Like if everyone's saying, you know, we have to do an all wood mass timber building, ask why. I mean, the most magical question is why. And as Simon Sinek says, 5 whys. You ask why, and then when you get the answer, ask why again, and then ask why and why. And you should sort of be able to boil it down to like, what's the real reason here? Because I think if we just said, well, it's got to be all wood, we would never come up with the idea. But the real purpose is we want to lock up carbon in wood. That's different. So ask why and examine the paradigms that we're stuck in. And it's very hard to do because we're stuck in them. So that's what I'd say.
Right. Well, it was great getting a chance to talk with you today. I'm really glad that you were able to make time. And, you know, I'd like to thank everybody for listening in on this. And, you know, I hope all of you have a great rest of your day.